one of the most popular, or maybe I should say the most popular visualization of the interiors of the neural network has been proposed in this paper at 2016, which is known as the classed activation map, or CAMS. So this idea, once it was proposed, it was so popular that all the people who were working in this field were trying to see inside what is happening in the neural network through these concepts. And in fact, around 10 versions or 10 variations of CAM were proposed in the last few years since 2016. So let me explain what is this class activation map all about. Okay, the let's say you trained a network and it has something like this. You pass an image through various convolutional layers. Of course, the size of the image gets reduced, but the number of channels may get increased, and you finally arrive at the last convolutional layer of the network. And after that, you typically has either flattening or the average pooling, and then you have the fully connected layer here, and then you have the classifier head here. Okay, so for some numbers, you just take the ResNet case and you have 2048 channels, and 7 cross 7 is the resolution of the last convolutional layer. And once you have the global average pooling, you collapse, you basically sum over the pixels, and you end up in getting 1 cross 2048, and this we named as the embedding, or the final feature space, or the manifold, or the bottleneck layer of this particular guy, or this is the feature representation of this image, we can say 2048 dimensional feature representation of this image. And once you have it, you have certain weights which will be adding up to have that final layer, and this is like the 1 cross 1000. In the case of ImageNet, we have 1000 of such cases. Okay, now the interesting aspect here is, first you look at here, how are you arriving from here to here. So here, for example, we have first layer, first channel in the convolutional layer, and you are going to kind of average over all the pixels, and you have one value, and that's what happening here. Similarly, the second layer, you average for all the pixels, basically the 7 cross 7, you sum it up, and that value is represented here. And the final one, of course, again is averaged over all pixels, and that value is represented here. That's how you get 2048, right? Because this dimension is 2048, and if you see here, this is 7 and this is 7. So this dimension is collapsed, and for each of the channel this is collapsed, and that's how you arrive at these positions. Okay, now if let's say I'm interested in a particular class, in this case Australian Terrier, which is the breed which is lying here. Okay, so I want to kind of uh, have this class. So I only consider this class, and then if I choose this class, I only consider the weights associated with this class, which is linking the final uh, fully connected layer to the classifier layer. Okay, now what I'm going to do is interesting. So this W1 I will use to weight the corresponding convolution map, which is this guy. Okay, so W1 multiplied by this convolution map, that is what we are showing here. So this W1 is coming from here, and this guy is this first guy. Then you take the second guy, let it be like this, and you take this W2 and weight it. And similarly you do it for all others, and the final one, this is Wn, and the final layer is actually here. So then you sum it up with that weights. Okay, so you W1 multiplied by this plus W2 multiplied by this plus so on till the final layer, and you have one particular guy over here. So effectively what you have done is you collapsed this 2048. So you have a 7 cross 7 image, or 7 cross 7 feature here, which is a weighted sum, and the weights are coming from the connection weights between your desired class and the fully connected layer, and the convolutions, or the 7 cross 1 7 is coming from the convolution maps. But of course this is not the same size as your image, so you need to upsample this to the image size, let's say 224 cross 224, and then you can overlay on the image, and it looks like this. And what you are seeing over here, this is predicting as Australian Terrier, and that portion is kind of highlighted, and this is known as the class activation map. So the class, then you see the activations, and you're creating a map out of it. Okay, so that's the full picture. So I have the explanation again, or the steps again, in the next slide, so I'm not going to explain that now. But mathematically what is happening is, so you have fk of xy, which is one of these layers. K stands for the kth layer, so k is 2048 here, 1 to 2048. and xy is the pixel 7 cross 7 here. So what you're going, how are you getting this guy is basically you sum over all the pixels, right? So that's the case. So kth one, so this guy is coming from the first, this guy is coming from the second, and so on. Okay, and then after that, this operation, what is happening here, so you have a class here, this is the class, so you're basically weighting the fk's. So this is the fk's, which are these guys, right? So those are weighted by the respective weights here, and then you sum it over, you get a class. So k is basically again uh, the the uh, the feature here, okay, the feature weights here rather. Okay, so now let's interchange it. The summations I just interchanged it, so k goes in and xy goes out, and this part is basically exactly what this part is all about. Okay, and we don't do this, and that's what exactly the CAM is all about. So we ignore this, but this part is exactly kept as it is, and this is basically the mathematical derivation for the class activation map. So let me remove the ink from here, and this slide, yeah, of course, the important drawback I would say is like the weights have to be available, and that means the model has to be fully trained, or the model has to be trained with reasonable accuracy so that you can trust on these weights. And the advantage of course is there is no backward propagation here. This is only once you train the model fully, just the forward pass is good enough, because we just need to extract the weights, that's all. Okay, so the steps again, so identify the class, whatever class you are interested in finding the activation map. So that's the first step, because the class is important. And then you extract the weights corresponding to the class. So we, in the case of ResNet 50 for example, you have 2048 weights corresponding to that particular class, right? And then you use that weights to multiply the convolutional layers, typically the last convolutional layers, and then you may want to pass it through the ReLU layer so that the negative values are all gone. And then you sum it up to get one activation map, but that map may be of less dimension or less resolution, like 7 cross 7. So you need to upsample it to the original image size so that you can overlay on the image and see the result. So this is an interesting result presented in the original paper on class activation map. So this is an image of a DOM, but the model is predicting it as palace. And if you choose palace as the class and create the class activation map using these steps, what you see is over here, the focus is actually on this region. And if you, as a human, if you don't see this and only see this region, you will also predict it as a palace, right? So the model is not doing a bad job here, and in fact it is telling you, it is explaining you why it is predicting it as palace, and that's the beauty of class activation map. Now if I use DOM as the class and recreate or regenerate the CAM again using these steps, what you're going to see over here is the focus will be on this, and that makes sense. And similarly, if you consider these two, maybe you get misinterpreted as church and so on. So this is a very powerful technique in that sense. So uh, I will show the Colab demo maybe at the end so that we can go everything together. But let me go uh, to the next obvious step. So the major drawback in the case of class activation map is like the model has to be fully trained. And that's where people thought about and developed this technique known as gradient weighted class activation map, or commonly known as GradCam. So the idea here is very simple. So let's not wait for the entire model to get trained. Rather, let's use the back propagation to get the gradient weights and use that to generate the class activation map instead. So the idea is not very difficult. Let me explain to you in a moment. So the first step is of course the same. You identify a class that you want to kind of see the activation map. So once that class is kind of identified, you of course need to do a forward pass, and you extract the activations using the forward hook, maybe the final convolutional layer as we saw in the previous case. You don't stop there. So previously you stopped there, and then you are using the weights here to weight these maps and sum it up and get the class activation map, but we are not going to do that now. Instead, you're going to do a back propagation with this class, whatever desired class as 1 and all other classes as 0. You can do the back propagation till the desired layer, which is actually the last convolutional layer, and these are nothing but the gradient equivalent or gradients for the convolution map. So the dimension will be exactly the same, let's say 7 cross 7 and 2048 of them, same as this. The only difference is this is activation and this is the gradients. Okay, and what we are going to do now is the process similar to the previous case, where you going to collapse the first gradient, you sum it over all pixels and use that as a weight. Similarly, the next layer or next channel rather, you sum it over all pixels and find that weight, and similarly you do it for all the case, so you find the weights. So previously these weights were coming from the weights over here, which were the trained weights, but now we are extracting these weights from the gradients. Once these weights are identified, you do that multiplication, the weighted multiplication similar to the previous step, and you kind of sum it up. You get a single map which is kind of 7 cross 7. You pass it through ReLU so that negative values are gone, and then you upsample it to 224 cross 224, and you have the same sized gradient weighted class activation map now. So the major difference is, earlier we were using the trained weights as the weights for summing up the feature maps, but now we are using the gradients, the weights derived from the gradients to weight the convolution maps. Okay, and we can also do another thing. We can propagate the gradients all the way back to the image, just like the saliency map we generated using the gradient. So the interesting part on that is, you have chosen a class and the gradients are back propagated for that class, and if you multiply this guy with this guy, you get something like this. And you see here, the if you guess this, it should have been the class cat which was chosen here. So if you choose the class dog, it probably will be highlighted here. Okay, so just to summarize the steps here. So you set the class which is the desired class to 1, all others to 0, and then you need to do a forward propagation also, which is not mentioned here, to get the activations at the desired convolutional layer, which is obviously most probably the last convolutional layer in the network. And then you do a back propagation till the convolutional layer and get the gradient maps corresponding to that particular convolutional layer. So now sum over all pixels for each of these gradient maps to generate the weights, and use that weights to weight sum the feature maps or the convolutional activation maps, and then of course pass it through ReLU to remove the negative values and resize, and then you can overlay on the image. And an optional step, as I said, you can back propagate all the way up to the image and then use that to come up with something known as guided gradient cam. And these are the results presented in the paper. So this is the original image, and if I use the gradients all the way back, it looks like this, and if I use the grad cam, it looks like this. So here the cat class was chosen, here the dog class was chosen, so the activations are correct. If I multiply these two, you can see that the cat is kind of isolated and the dog is kind of isolated. Similar results can be obtained using the saliency via occlusion technique. That results is shown here. So if I mask the face of the dog, it is going to be mispredicting this. Similarly, if I mask the cat here, it is going to be mispredicting this. But the problem with the saliency map through occlusion is, like, you need to run the mask all through the image, and that is going to be a computationally intensive task. But on the other hand, the guided grad cam is quite simple and is very easy to use as well. And this is the final one, is the result using the ResNet model, and the grad cam for cat and dog in the respective rows. There were variations, as I said, there were around 10 variations of grad cam, or cam rather, and one of them is cam plus, and this is actually very simple technique. I'm not going to spend a lot of time here. The major difference between the grad cam and grad cam plus is that the authors realize that the extent of, let's say, in the cat and dog in the image, the spatial extent of cat and dog is not the same. Maybe the cat is occupying more pixels than the dog, so we need to scale the gradients with the spatial extent. So that's the only inclusion that these people did and called it as grad cam plus, a small scaling factor which they added, which is based on the extent of the uh, basically this guy. Okay, there's no other difference between them. So of course this is a typical cam where these weights are used to weight, and this is a grad cam where the back propagation weights are used here, and the only difference between these two is the scaling factor. So again, I reiterate it here, the gradient activations are scaled by the spatial extent. And the interesting results are here. So this is the plus grad cam plus plus, and this is grad cam and grad cam and grad cam plus. So you can see from these figures that the grad cam plus plus is very useful. And a very interesting application is also shown here, where these activation points, the highest activation point, can be used to generate a bounding box, and that forms the object detection uh, uh, application as well. So maybe this is the next lectures will be on object detection, and this is really nice to see that the activation maps can be used as a seeding point for the object detection. So let me clear off and go to the final slide. So you can apply the CAMs. There are 10 variants of CAM which is listed here. This paper has all the details. You can do the self study, and you don't need to code everything from scratch. There is a beautiful library which has all these CAMs built in, and you can use that to generate your own CAMs like this. One interesting CAM which I didn't explain is the score CAM, and you can actually take a look at on your own. So before going to the conclusion, let me actually quickly show the CAM and GradCAM in Colab. Okay, so the first step is of course identify the target layer, and we should go back to the ReLU here, because I'm interested in basically the, yeah, I think it's fine. I think we can go with this, no problem. Okay, so you identify the target layer, you did the forward hook, and then you get the activations, and you can display of course as we did earlier. But the CAM actually tells you is like you need to weight these activations, whatever activations that you're seeing over here, with the final layer, right, with the final layer weights. So how do we get the final layer weights? We can actually get it directly. So fully connected layer and the corresponding weights we store in a new variable here, and this will be the size, because it's a full weight, so it will be having a size of, let's say, 1000 cross 240 2048 in the case of an ImageNet classifier, because you have 1000 classes. And now comes the next, the most important step. You should identify the class that you're looking at. There are two ways to go about it. One is you see whichever class is the maximum predicted class. So that is one option. The other one is like whichever class you are interested in, whatever. Okay. So either way, you can choose one of them. So the weights are actually displayed here, which is not really needed for you. And then what you need to do is you need to multiply the weights with the corresponding activations, and you kind of sum it across. And then if you visualize that, of course you have to resample it, which is actually doing it using the cv2.resize. And if you display it, you can see that while the network is predicting it has platypus, it is looking at this region in the image. So this is the simple CAM. Now for GradCAM, what we need is, in addition to the forward activation, we need to have the back propagation to get the gradients, because we are going to estimate the weights from the gradients, right? So here is the back propagation code. So you are registering a backward hook here. The function is same, you remember that. Then we do a forward pass, and then you do a backward pass, and the gradients are extracted out, and then you multiply the gradients with the activations. Of course, the important aspect here is the class. We need to identify the class, which I am just chosen one class for reference, and if I do that, I get the GradCAM now, and I can display it. Okay, so that's all. And just to conclude, visualizing the layers of CNNs is an important task, because that helps in the explainability of the model, why the model is working. We can get a lot of information, a lot of intuition by looking at the layers of the CNN. And we also talked about various filters. You can in fact extract any layer of the neural network and display them as images. For example, we can visualize the final layers. PCA and TSNE were the friends. We can use that for many purposes. So three purposes we described. We can use it for finding the regions in the image where the activation is looking at. We can use it for saliency, or we can use it for the class activation map.